All right, so we're going to see if this works.
All right, so what I want to do is, I appreciate all those who have sent me feedback about the class, either through email or through the survey. We are now moving to a new unit. We've finished the linear programming unit. What we're going to be doing now is doing fixed point theorems. Fixed point theorems are some of the most important results in mathematics and applications, especially economics. And so, based on your comments, what I want to do is I want to try to hit every single category at the same time, which is going to be a hard challenge because a good chunk of you want more theory and a good chunk of you want less theory, a good chunk of you want more applications, a good chunk of you want less applications. So this is the either half full or half empty part of the semester. Okay, so I can't hit everything simultaneously, but I will try to make sure that every request is hit significantly. There are 3 proofs in the book on the Brouwer fixed point theorem. The first is basically a Calc 3. I chose not to do that for several reasons. The most important being people's Calc 3 is often, I'll leave it at that. The one I chose to go with uses Sperner's lemma. And Sperner's lemma has a lot of very interesting applications. It's a really nice combinatorial result. It leads to a lot of good things. And so I thought if we use the Sperner lemma approach, then this could be a good introduction to some really good theoretical mathematics that you can use for other things. How many of you have seen the movie War of the Roses? Okay. It's probably as funny of a movie you can get about a couple having a very vicious divorce. And so I think it's Kathleen Turner and Michael Douglas are married. Danny DeVito is the lawyer of Michael Douglas. And everything starts off fine and dandy, but then over time things devolve. And he and his wife are having an extremely messy separation. And this is actually related to Sperner's lemma. Okay? So this is not a stretch. This is not just a justification like I did with Father of the Bride to play one of the movies I like in class. One of the best applications I know of Sperner's lemma is the rental problem. And this will be useful for some of you who are graduating in the near future and are going to be going to cities and sharing apartments with people. How do you determine who pays what rent and who gets what room in a setup like this? And so there's a great paper by Francis Su that we will talk a little bit about in class, or at the very least I will put it on the webpage for you to look at. And it uses Sperner's lemma to figure out if you have a bunch of people who are sharing an apartment, who gets which room and how much do they pay for it in such a way that everybody's happy. So this falls under the category of fair division. How many of you have ever taken a class with fair division? Okay, if everybody likes everything the same amount, it's very easy to divide things fairly. But if different people have different preferences, all of a sudden, this becomes an extremely difficult problem. What is the optimal way to divide a resource or a set of resources to maximize happiness? And then similar to the medical school problem that you're looking at, are we trying to maximize total happiness, or are we trying to minimize the person who is the least unhappy or the most unhappy? Lots of different ways you can look at problems like this. One of the best applications of this is divorce proceedings, when you have marital assets that are trying to be divided. And so in this scene, Kirk Douglas is talking with his lawyer about how he and his wife are going to be dividing up their house. So I think I have to walk like this so the camera doesn't track me. Oh, good, it worked. All right.
Can't have one. When a couple starts keeping score, there is no winning. It's only degrees of losing.
I am the one who found this house. I bought everything in it.
With my money. It's a lot easier to spend than it is to make it, honey bun.
You might not have made it if not for me, sweet cakes.
Never underestimate her as an adversary. Don't even talk to her, bitch.
Come.
Filth. The yellow areas are mine. The red areas are hers. This seems rational to you both? I got more square footage.
All right, so most people, can you turn on the light? I'm not going to get to the point where they will be dividing the square footage of their house with their former partner and trying to figure out, how can they get more square footage. But the idea of dividing assets is extremely important. And again, it's not just for stuff like marital assets. You have a bunch of resources and you're trying to decide how to allocate them. How much do different people feel for this? there is one issue that I want to talk about before we go into the mathematics part of this lecture. Can you trust people when they tell you their evaluation? Any baseball fans here? Any Red Sox fans? Anybody remember the Red Sox signing Crawford a couple of years ago from Tampa Bay? The Yankees pretended to be interested in him to drive up the price and get the Red Sox to spend more. It was beautifully done by the Yankees. They got the Red Sox to enormously overpay for somebody. And so when you have situations like this, you cannot always trust the value assignments that people make. And so this is very similar to the people who are looking at Math Blast right now in terms of what can you do when you can't trust the data. In theoretical math classes, we always assume the data is accurate. We don't have experimental error. The second prime is 3. This is known. So these are real issues that you have to consider. All right, so what I want to do now is I want to segue into contraction maps, fixed point theorems, stuff like that. We already talked a little bit about fixed point theorems in one dimension. We talked about the intermediate value theorem. We'll prove an example of a fixed point theorem in one dimension. We'll see how easy it is, and we will weep at how hard it gets when we go beyond one dimension. I'll talk a little bit about Newton's method. How many of you have seen Newton's method before? If you're not enjoying the class, this is the problem that actually made me a mathematician. I was on the fence between math and physics, and when I saw this problem as a sophomore, this is what convinced me to do mathematics. It's incredibly powerful. All right, so let's do fixed point theorems. And so again, I am wearing this shirt so I remember we are in a situation with no transportation. Okay? We must have continuous functions. If you have discontinuous functions, of course all hell can break loose. So f is continuous. F is going to map 0, 1 to 0, 1. Then there exists an x such that f of x equals x. Proof. So here's 0, here's 1, here's 1, here's 1, 1. What do we know about f of 0? It's somewhere between 0 and 1. Can you narrow it down any further? What can we assume without loss of generality about f of 0? Or what would make this problem trivial? Yeah, if f of 0 is 0, it's not so hard to find a point such that f of x equals x. So case 1, f of 0 equals 0. Okay, case 1 is not hard. We found the fixed point, right? Fixed point is 0. What do you think case 2 should be? I'm sorry? One possibility, what is greater than 0? Well, not x. X is an arbitrary point. What do you mean by that arbitrary point? So case 1 was, f of 0 is 0. What should case 2 be? What's a good thought for case 2?
F of 1 is 1.
Good, f of 1 is 1. Is it easy to find a fixed point in this case? Yes. Fixed point is 1. Are these cases mutually, can these cases happen simultaneously? Is that okay? Sure. Right? I don't need the cases to be disjoint. I just need the cases to be exhaustive. I need to exhaust all possibilities. If I happen to have a function that's 0 at 0 and 1 at 1, great, I have 2 fixed points. I can now assume that f of 0 is positive and f of 1 is less than 1. So case 3, f of 0 is greater than 0, f of 1 is less than 1. And I have some function like this. And the claim is that the only way I can have this is I have to cross at some point. So let's let g of x equal f of x minus x. What can you tell me about g of 0? It's positive. What can you tell me about g of 1? It's negative. Therefore, the intermediate value theorem implies there exists a c such that f of c equals 0. Right? If it's positive here and negative here, there has to be an intermediate point where g is 0. What does it mean for g to be 0? G of x is just f of x minus x. That's our fixed point. So since g of c equals 0, that implies f of c minus c equals 0. That implies f of c equals c. That implies c is the fixed point. And that's the proof of the fixed point theorem in one dimension. Okay? So in one dimension, it's not that bad. It is amazing how much worse it's going to get in several dimensions. It's just the intermediate value theorem. Has anybody seen a multidimensional generalization of the intermediate value theorem? You always want to get a sense of what is being used and where do these proofs break down. Can we generalize it? Okay. So what I want to do, now that we have a fixed point theorem in one dimension, I want to talk about Newton's method. Versus divide and conquer. And this is a great way to illustrate the differences in techniques in terms of what you can do. Now, we just proved the existence of a fixed point. Are you happy? Hopefully you're at least a little happy, yes. We don't know where that fixed point is. It would be nice to know where the fixed point is, but we at least know that there is one. So if we try to search for it, we can be guaranteed that there will be one to find. Okay? And we talked about earlier how instead of trying to find fixed points, if you want to solve equations, if you want to know where is the x such that f of x equals a, we talked about how to convert that to a fixed point. So really looking for fixed points is equivalent to trying to solve equations. So it's nice to know a solution exists, that's step one, but step two is then we want to find that solution. And so what I want to do now is I want to give you a constructive method to find the solution. And again, there's a limit to which algorithms we can analyze in full detail in this class. This is a situation where I can give you some of the analysis very easily for one of the cases, and for those of you who are interested, I will give you a homework problem that's optional that just outlines how you would analyze how fast Newton's method is. I think we've talked a little bit about divide and conquer. I gave you the birthday, guessing someone's birthday in 10 questions or less. Have I given you this one? Okay. I can figure out your birthday in 10 questions or less so long as you do two things. You answer honestly, and if I'm wrong, you tell me if it's earlier or later in the year. All right? So, birthday in 10 questions. What's my first guess? July 1st, maybe June 30th, something like that. I would probably go with July 1st because February is a little bit short. We have July and August both having 31 days. I like July 1st. Is there anybody who wants to play the first few rounds? I can. Is it July 1st? It's after. So now what should I do? The midpoint. So July, August, September, so maybe October 1st. October 1st. Before. And so now we know it's somewhere in here. So every time we ask a question, we have the uncertainty. So each iteration halves the error. That's not bad. instead of doing this in terms of birthdays, what we could do is, let's say we have a function, and we want to try to find where's the function 0. So here's the interval 0, 1. Let's say the function is positive here, and the function is negative here. There must be a root between the two of them. Why must there be a root between the two of them? Intermediate value theorem. So my uncertainty as to where the root is 1 unit. I now go halfway at 1/2, and let's say it's positive there. Where must the root be? The second half. So now I go at 3/4, and let's say it was negative. Now I know the root is somewhere between these. Every time I iterate, I have my uncertainty. That's not bad. 50% improvement every single time. So the big number to know, what does 2 to the 10 equal? Yeah. Wait, question?
Yeah, what if you have more than one root on your own?
So if you have more than one root, you don't know which root you'll go to. The other problem is if you have a double root that just hits the x-axis, this could miss a double root because it'll be positive on both sides. So in terms of stability issues, if you have a double root, there's problems, or any root of even degree. And again, you don't necessarily know which root you will converge to. So I'll put up some pictures on fractal geometry where you have methods like this, which hop between the roots they go to. So what does 2 to the 10 equal? 1024. And 1024 is approximately 1,000. So this is why in computer science, how many megabytes are in a gigabyte? 1,024. Yes.
Can we do 9 questions?
This is to cover your, in case you make a little bit of a mistake, in case you average things a little bit off. This gives yourself a little bit of leeway. You're absolutely right that if we're trying to guess birthdays, we don't need 10 questions. We should be able to do it in 9. But with the little kids that I do this at parties, they don't really know the difference between 9 and 10. Gives you a little bit of freedom. You can make a small mistake, and you don't have to be as careful when you're coming up with these divisions. So in computer science, when you look at how things are named, going from megabyte to gigabytes, that implies a change of a factor of 1,000. Well, 1,000 is almost 1024, and so they use that notation. So another way of looking at this is every 10 times you do this method, you gain 3 decimal digits. 10 attempts gives you 3 digits. Good or bad? So every 10 times you do this, you will gain 3 decimal digits. If you want a number to 10 decimal digits, how many times do you have to apply? 40 would be a little bit high, somewhere between 30 and 40. So, it's nice, you'll be gaining more and more digits, but it will take a while to get incredibly high accuracy. You may not need incredibly high accuracy. What I want to do now is show you Newton's method. How many of you have seen Newton's method? Okay, this is one of the greatest algorithms that we have. It is incredible how fast it is. It is going to destroy divide and conquer. The reason it's going to destroy divide and conquer is it's going to use more information than divide and conquer. What does divide and conquer use?
Just the values of the function.
Just the values of the function. So we're assuming something about the function if we're using divide and conquer. What are we assuming about the function? It's continuous. So here, divide and conquer, we're assuming continuous, as we need the intermediate value theorem. The intermediate value theorem is the key ingredient in the proof, so we need to assume continuity. Was there a question in the back? Okay, so we're going to assume more. We're now, f is continuous f is differentiable, and just to be safe, I'll say f is continuously differentiable. And this is a much stronger condition than just assuming continuity. Not surprisingly, if we assume more, we can do more. And so the question becomes, what can we do now with this assumption? So let's look at, I'm going to do it for a specific example. Let's try to solve for the cube root of 3. And so I'm going to look for the function f of x is x squared minus 3. And if I can find a 0 of this function, I'll have the square root of 3. How many square roots of 3 exist? 2. I'll aim for the positive square root. Okay? So let's look at what's going on. Square root of 3 is approximately 1.7. And so this is not quite drawn to scale. So here is 0. Here's square root of 3. Here, let me draw a little bit better. Just want to really emphasize the next step. Okay. Somebody give me a reasonable guess for the square root of 3. Not a great one, but a reasonable one. That's too good. Oh, that's too bad. I mean, we can do a little bit better than 1, 2. Right? So we start where we guess x naught equals 2. Yes?
If we have more complicated problems, how does the algorithm know where to start?
You need to give it some initial input. And one of the big questions is, where will the algorithm terminate? And this is,
It'll converge anyway.
it doesn't always converge, unfortunately. So this is where you get a lot of fractal geometry and fractal pictures in dynamical systems, is that in complicated systems, it can actually hop between roots. And if you change your initial guess by like 10 to the negative 1,000, that's enough to change where you go. It has extreme sensitivity to initial conditions. So this is a great way to see some of the issues that are out there. Now, in the real world, we do not know anything to 1,000 decimal digits. We don't have to worry about something like that. So the idea is to start off with a reasonable guess, to show you that I'm not cherry picking things. I'm not taking a phenomenally good one. I'm not going to be horrible and take 1. I know I can do a little bit better than 1. 1 squared is 1, 2 squared is 4. 4 seems closer to 3. So let's start there. And the way it works is the following. So you start off with your initial guess. And so I have the point 2, f of 2. And then I have the slope of the tangent line, which is f prime of 2. You can distill a huge amount of calculus into the following statement. If the function is not linear, make it so. Replace nonlinear functions with linear functions. This is the whole theory of Taylor series. If the linear function is not doing a good job, what do? Instead of replacing with a linear function, you move on to quadratic. And you do a second order Taylor series. The idea is you replace complicated functions with simple functions. The benefit of using a linear function is it's very easy to work with. A quadratic function, a quadratic, would do a much better job, but it would be a lot more work. Let's see what we can get by just using a linear function. So let's pretend that the tangent line is identical to the function. This is not true. Okay? But let's just pretend it is. Well, if the tangent line is equal to the function, I can look and see where does the tangent line hit the x-axis. And that should be a good approximation to the root. Then it turns out, oh crap, it's not the root. So then we use the lather, rinse, repeat method. Right? We now take this as a new guess, and we come up here, and now we draw the new tangent line. And this is actually drawn to scale. It really is this good that by the second iteration, we really can't even tell a difference anymore. So let's go through this formally. So the tangent line, let's do a general point. We have the point xn, f of xn. And and we have the slope f prime of xn. So now we get y minus f of xn equals f prime of xn times x minus xn. And we want to find the place where this line hits the x-axis. So when it hits the x-axis, what do we know about y? It's 0. So xn plus 1 is when y is 0. So we get negative f of xn equals f prime of xn, xn plus 1 minus xn. And so if we solve, we get xn plus 1 is equal to, bringing things over, xn minus f of xn over f prime of xn. Okay. And here is a formula to calculate the values. Okay? So this is not a very difficult formula. So what I want to do now is I want to go back and I want to show some things. Okay. You want to, let's see. See, this is, all right. Let's see. Is this clear enough to see? Yes? Cry. Okay. Actually, you want to turn off the light? Thanks. All right. So let's look and see what's going on for some values. So I'm applying Newton's method to find the square root of 3. And so this is just a very simple code, and at the end it's going to print out the square root of 3. So I'm doing the first 4 iterates where my initial guess is the 2. So what's really nice about this is you actually get rational numbers. So when you do the algebra, and I encourage you to do this at home, you get 7/4 for your first answer. You get 9756 for your second, 18,817 over 10,864 for the third. I'm not even going to try to read that one. Okay? Let's look at the numerical approximations. I'll just put them all up at the same time. Here is the square root of 3. All right? So the square root of 3 is 1.320508075688771931766604. What do we get after 4 iterations of Newton's method? The great Richard Feynman once remarked about how phenomenal quantum mechanics is. And one of the things he said is, quantum mechanics is so accurate, it's the equivalent to measuring the distance between Los Angeles and Boston to within the thickness of a human hair. We really don't have much of a need to know the distance between Los Angeles and Boston to that level of accuracy. When you're getting your frequent flyer miles, they don't need it that accurate. Right? But if you try to figure out roughly how accurate do you think that is to be within a human hair? 10 to the what power? What fraction of the total distance do you think we are? How far is it roughly from Los Angeles to Boston? 3,000 miles. All right. How much of a mile do you think the width of a human hair is? All right, so an inch is 5,280 feet. Okay. So we're trying to figure out what we have. So we have 3,000 miles. Call it 10,000 miles, right? 10 to the 4th miles. How many feet in a mile? Okay. 5 times 1,000. And then how many inches in a feet? Yeah, we'll call that one. I mean, we rounded everything up. Let's at least not round that one up. All right. What fraction of an inch do you think a human hair is? 1,000? So you think 1,000 human hairs would make up an inch? Is everybody comfortable with that, or do you want to do 10,000? You happy with 1,000? All right, 3, 6, 10, 11, about 5 times 10 to the 11. That's roughly correct. Order of magnitude, yes. So essentially, quantum mechanics is measuring things to 11 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I've lost track over 20. In 4 iterations, this is better than what we're getting in quantum mechanics. So in terms of the power of this algorithm, how rapidly it converges, this is phenomenal. And you can prove that it converges this fast. So for those of you who want some additional theory, I will give you a guided set of problems on this. This is the problem that made me a mathematician, is when we got this. Basically, every time you apply Newton's method, you don't have your error. You double the number of decimal digits accuracy you have. And you do it with a rational approximation. So for those of you who like to program, working with rationals is nice. Question?
What happens if you choose an awful initial value?
Then it takes an extra turn or two before it becomes good. And there is a danger that you could go to the root other than the root you want. But here, the first approximation, 1.75, is not so bad. The next one, 1.73214, all right, that's not horrible. The next one, we've already got the 508.100 versus 508.075. This is phenomenally fast. Okay? So I write a lot of letters of recommendation. If I could choose an algorithm to write one for, I would choose Newton's method. Okay? It is phenomenal how quickly this works. When you compare this to divide and conquer, it's night and day. You sweat through 10 more iterations of divide and conquer for 3 decimal digits. You do another 10, and you get 3 decimal digits. You talk about comparison of runtime. And again, it is not a horrible set of problems, but these problems come from a real analysis class. And as real analysis is not a requirement for this class, I do not want to do that in the class proper. I will instead just make these available. And if you have any questions, I'm happy, as you can tell, to discuss this subject. Okay? You can actually write down an explicit formula for xn plus 1 in terms of xn and the values of the function without too much trouble. And you get this beautiful recursive formula. Okay. So again, lots of wonderful applications. Is there an extra light that you've turned on? Another extra light you've turned on, maybe? Because all of a sudden, there's a much greater glare than in any other time in the semester. You want to just try hitting a few light switches and see if you can decrease the glare? Okay, okay, now put some of the ones, okay, put them back in the front. Try to optimize the lighting, please. All right, that's good. That's good. That's good, thank you. Okay. All right, so the first half of the lecture may not be viewable, but oh well. Okay. So, again, the big lesson to draw from this is the more you assume, the more you can get. Not surprising. Okay? Continuing on this, so the lesson, more assume, more obtainable. This leads to contraction maps. Most maps are not contraction maps. Most functions are not differentiable. One of the big, there's many lies that you've been exposed to in your undergraduate career. You tend to think most functions are differentiable. Every now and then you have something like a non-differentiable function, such as absolute value. But if you think about the absolute value function, come on, okay. It's not differentiable, but it's only not differentiable at one point, right? It's almost differentiable. In the spirit of Princess Bride, right? It's almost differentiable, mostly differentiable, right? Turns out that you can put a measure on the set of all possible continuous functions, and it will turn out that almost any continuous function is differentiable nowhere. It's very hard to find a continuous function that's differentiable, even at one point, if you just sample randomly, uniformly from the space of all continuous functions. Fortunately, almost every function can be well approximated by a continuous differentiable function, so it's not a big deal. But most functions are not differentiable, even at one point. Most maps, most functions, are not contraction maps. But just as we saw with Newton's method, if you assume more about your function, if you assume in addition to being continuous, it's also differentiable, you can prove a lot more. The same is true in terms of trying to prove fixed point theorems. If we assume that the function is a contraction map, not only can we prove a fixed point theorem, but we can find a way to discover where that fixed point is. So we say f from S to S is a contraction map if there exists a C strictly less than 1 and positive, because we never assume negative constants, such that for all x, y in S, f of x minus f of y is strictly less than C times x minus y. The book talks about more general metric spaces, and so what you might do is you might put in double lines here to say, I'm talking about the distance between things. Okay? We often overload the symbol for distance and just use the absolute value. So if I give you a vector 1, 2, 3, what would I say is the absolute value of the vector 1, 2, 3? Right, so if I give you v is 1, 2, 3, the absolute value of v, which we might write with two norms for the norm of v, is the square root of 1 squared plus 2 squared plus 3 squared. So that would be the square root of 14. So we often overload symbols in mathematics, and we'll extend the notion of absolute value to apply to a more general space. So we want some space S where I can talk about a notion of size of objects. Basically, I want to know how far away am I from something. So this leads to the notion of a metric space. Okay? And so, can somebody interpret in words what this means? What does it mean for f of x minus f of y to be less than c times x minus y, where c is less than 1? Tell me a story. If you want, I can tell you a story. Cam starts off at x and Kayla starts off at y. In order to make sure my kids don't fight, whatever I do with one of them, I must do to the other. I apply f to where Cameron is and f to where Kayla is. Cameron is now at f of x, Kayla is now at f of y. If they were initially this far apart, how far apart are they now? F of x minus f of y. What happened to the distance between Cam and Kayla? It grew by a factor of c. Now, since c is less than 1, instead of saying it grew by a factor of c, it shrunk by a factor of c. It dilated, it changed by a factor of c. This is why we call it a contraction map. When you apply it to 2 points, and you apply f to it, we don't know where f maps them, but we know the distance between them gets smaller. Well, if we've done it once, what can we do? Lather, rinse, repeat. It's one of the most common methods in mathematics. Keep applying f. What will happen to this chain of points? Well, if every time we apply it, the distance between them contracts by at least a factor of c, if not more, then what's going to happen in the limit? They're going to converge to the same value. Now, one thing that we don't know yet is maybe as we apply it, they start getting closer, and they get closer over here, then they get closer over here, then closer over here, then closer over here, and they're moving in some kind of cycle. And they're getting closer to each other, but the points are not converging to any particular point. So we need to do a little bit of work to prove that this converges. And so this is where the course becomes a little bit of an introduction to real analysis. So this is a pre-core class. I'm not expecting you to be able to independently do arguments like this, but I know a lot of you have seen real analysis, and this way I can show you a little bit about how you would make arguments like this rigorous. For those of you who have not taken real analysis yet, a lot of you are math majors and you will eventually be taking real analysis, and this is putting a little bit of material in the bank. and getting a sense of why classes like real analysis exist. They exist in order to make arguments like this rigorous. Okay? So I'm not going to go through the details right now. Instead, I'm going to just do one last thing of showing how we can apply this to solve our problem. And then we'll go back and prove. So consider the question, given a contraction map F, where is its fixed point? The way I've written this question, I'm assuming a couple of things. What am I assuming from how I've written this? There is one, and I'm even assuming more than there is one.
You can find it.
Technically, I'm not assuming that. I want to find it, but I'm technically not assuming I can find it. There's only one. So theorem. If there exists a fixed point, it is unique. Okay, we have time to prove this.
Is this only for contraction?
This is for contraction maps. And why would you consider any other map? So proof. Any thoughts about how we might try to prove this? What technique? Assume there's more than one. If you look at what's going on, the contraction map, it was really nice to take 2 points and apply F to them. So we saw we got a lot of information by taking 2 points and applying F. Let's assume there's at least 2 fixed points. Assume x1 and x2 are fixed points. Then the absolute value of f of x1 minus f of x2 is strictly less than c times x1 minus x2. And c is less than 1. Well, what do we know about f of x1? It's x1, f of x2. It's x2. So we get this beautiful fact that x1 minus x2 is strictly less than the absolute value of x1 minus x2. Is there any number whose length is strictly less than its length? No. Contradiction. In the scheme of things, this is relatively easy. If there's a fixed point, it's unique. Okay? Now, we don't know yet that there is a fixed point. That's the next part of the proof, is to show that we can find a fixed point. Okay? So now the question becomes, how do we find the fixed point? So as we're about to end, yes?
What happened to C? Because technically couldn't it be less than if C is shrinking it? Because, oh no, actually.
Right. So this is a very important point. So C is fixed. And so because C is fixed, it's the same C every time we apply. It's the same C independent of points. Okay. And so if you might start off where given any point x1 and x2, there is a corresponding C. Maybe you have some kind of compact set. You can then look at all the C's simultaneously and choose some kind of supremum of the C's, use a lot of real analysis. We will just assume that we are given a function where we can immediately tell that there is such a C. And the key fact is that it's a C that's strictly less than 1. There's a lot of mistakes that are made where you have a map where f of x1 minus f of x2 is strictly less than x1 minus x2. That's not a contraction map. The difference with that is it's a different C for each pair of x1 and x2, and those C's could be approaching 1. What would happen if C equaled 1?
If you kept taking the function over and over again, it's bounded below and it's decreasing, so it would converge. The distance between the conversion, not necessarily.
But not necessarily to 0, and that's the problem. Is if it's getting close to 1 astronomically fast, maybe at the nth stage it's 1 minus 10 to the negative n factorial. So it's really rapidly converging to 1. If you have a situation like that, you could actually have the distance converging to a non-zero number. All right, so because it's 1050 right now. I will just state how you find the fixed point. Choose your favorite point in S, your least favorite point in S, a random point in S, it doesn't matter. Choose any point in S and keep applying F. The theorem that we'll prove on Monday is that no matter what point you choose, you will end up at the unique fixed point. And so not only is it an existence proof, but it's actually a constructive proof.